In the previous lesson, we learned a little bit about hacker theory and how an attacker might approach developing threat models against an application. Let's dive into a more concrete example about the kinds of things that an attacker would be looking for during the enumeration phase of their security test. Welcome to the Cyber Scavenger Hunt, which you can find at cyberscavengerhunt.com. Cyber Scavenger Hunt is a web application written in React that further explains hacker theory within the context of a real web application. Here we are at the start of the Cyber Scavenger Hunt, where we can see that reconnaissance against a web application begins with the text of the website itself. We can start by opening up hint number 1. Many web developers are going to be familiar with the answer to this hint, which is, if I were a search engine, I'd look here to make sure I don't index any content I'm not supposed to. This has everything to do with search engine optimization. And looking at hint number 2, this is one of many examples that developers unwittingly use to tell Google what they don't want to appear in the search results. The problem here is not Google. The problem are the attackers. And the answer to this hint is robots.txt. Robots.txt is a file that explains to the Google search crawlers what content on the site should or should not be indexed for listing in the Google search results. And as we can see here near the top, there is a disallow/admin rule, which explains to Google not to index any content it finds on the admin page. But this is the first of the 8 Easter eggs that we will find on our cyber scavenger hunt. The problem with telling Google what not to index is that that content is exactly the content an attacker is going to want to enumerate. And it's very easy for us to add /admin to our URL and hit enter. This page is the second Easter egg on our cyber scavenger hunt. This is a fairly contrived example where an admin page may have been left exposed to the world. And certainly we didn't want Google to find it, but a malicious user certainly would be interested in looking at the admin page. Moving on from the admin page, let's look at our 2 hints to see what other information an attacker might use to find even more information about this application. Hint number 1 is going to point us to our browser's developer tools, which are as easy to use as right-clicking and moving down to Inspect, and that will open up a pane of developer tools that most internet users are unfamiliar with. Hint number 2 is going to be a bit more specific and telling us to look at the console within our browser's developer tools. The console can be found along the top. Clicking on console, we can find a message that has been left for us by one of the developers of this application. This is also the 3rd Easter egg on the cyber scavenger hunt. The message left by the developer says, what happens if we change the URL parameter authenticated to true? What you may or may not have noticed when we visited the admin page was that the application actually changed the URL to include an authenticated query parameter that is set to false. In this case, if we set it to true, we'll find the 4th of our 8 Easter eggs. And there's a good lesson here. Number 1, developers should not leave console messages in a production web application because very often those messages are intended for the developers to debug something specific. That information will be highly valuable to any attacker looking at a web application. Number 2, again, this is a highly contrived example where we're using query parameters to determine the authenticated status of a user. Most web applications won't have that. But the point here is that if you were able to get to a page that should have been properly secured, but perhaps wasn't for whatever reason, you might find links to other pages. Those pages are going to be used by an attacker to continue enumerating and gathering information. So from here, we can click on the Other Pages link, where we end up on yet another hidden page. And this is the 5th Easter egg on our cyber scavenger hunt. So developers clearly can be very careless. And if we continue to keep our developer tools open, let's look at the hints. Hint number 1 is looking for numbers like 200, 301, 404, or 500. If you're a web developer, you may already have an idea as to what those numbers are referring to. If you're not, let's look at hint number 2. Web servers often return lots of data that doesn't always get displayed on the screen. And as an example, we can go to the Network tab within our developer tools, where we'll see every request made by this web page to the server. And hint number 3 is asking us, is any of this making your header hurt? And again, if you're a web developer, this may indicate that there are various HTTP headers on the Network tab which would contain useful information for an attacker. Let's click on hidden.html, and we'll bump up the font size to make this a little bit easier to read. And what we can see here are the response headers being returned to us by the web server hosting this application. Sometimes the web server will make it very easy for an attacker to enumerate all kinds of information. For example, the fact that cyberscavengerhunt.com is hosted on Amazon S3, which again, going back to the previous lesson where we learned about the opinions of various frameworks or approaches to building web applications, we would immediately know anything hosted in Amazon S3 is probably a static asset. We can learn all kinds of other goodies from the headers here, learning that additional AWS infrastructure like CloudFront might be involved. Things like Amazon Code Build. As we continue on down through the list of HTTP response headers, we do find the 6th Easter egg on our scavenger hunt, which is telling us to continue looking in the Chrome developer tools, specifically for local storage for additional hidden content. Now, if you're unsure where local storage is, you can go to the Application tab of your developer tools, and you can open up local storage and click on the domain. And here we go. There's a key titled Egg 7, in which it tells us we found the 7th of our Easter eggs. Now, in this case, it's telling us to look for even more content within Chrome developer tools. So some part of the application is sticking information into the developer tools panel that we were unaware of just looking at the interface on the screen. So what can we find here? This Easter egg is telling us to look for a cookie, specifically one named Session. And if we look at the Session cookie, what we'll find is a value that is probably the most difficult item in the cyber scavenger hunt to figure out. If you have any background in coding values, or if you looked more closely at hint number 2, you do a Google search for base64 decode, and maybe we can find a way to decode the value that's in this cookie. Let's figure out what is here. We'll copy that. Maybe go to base64decode.org, or you can use any other number of base64 decoding tools that exist either on the internet or in various applications. We can type that data into our box. We can hit decode. And what we can find is the data in this cookie value was not actually encrypted. It was just encoded in a way that made it more difficult to see at first blush. The content in here is perfectly readable, and in fact, there's a great URL for you to go visit if you choose to do this example in your own time. This may be a bit of a contrived example because most applications that use cookies don't base64 encode the data within them. But stranger things have happened. And the moral of the story here is to make sure that any information that gets disseminated down to the client from the server, if you're going to use data that needs to be hidden in some way, don't rely on encodings that could be reversed. You're better off using a hash or an encrypted value of some kind that could only be decoded on the server. Let's recap some of what we just learned in the Cyber Scavenger Hunt. Number one, if you're going to use robots.txt, make sure that you're not simply telling Google to avoid pages because you've left them unsecured. You need to make sure that robots.txt is geared specifically for the purpose of mitigating any search results that appear in Google and are not trying to hide hidden content, because you cannot hide content from hackers. If you don't want them to see it, they need to be behind some sort of authentication mechanism. Make sure that you check any content that is being displayed in developer tools, specifically the JavaScript console, but also things that are coming back from the server, things like your HTTP response headers. It's very common for web servers to return all kinds of information by default, things that you can turn off, and you really should, so that an attacker has a much more difficult time identifying your infrastructure and the versions of software that you may be running on the server. And finally, any data that gets stored in local storage needs to be adequately protected. The examples I used were fairly contrived, and again, most session cookies are not going to be encoded using base64 values. But having said that, there are lots of things that do get stored in both session cookies or browser local storage, things like JWTs, that may be encoded, and that's an acceptable development perspective to have. You just need to be sure that there isn't any sensitive data that's included inside of that encoded data, because it is not encrypted and an attacker will decode that value to try to make sense of it. One final takeaway here for all of the cybersecurity professionals who are taking this course is to get super familiar with your browser's developer tools. And you need to think like a developer. Again, if you know the technology that they're using, whether it be React or Angular or PHP or Java or Amazon EC2 versus some other hosting mechanism, the more you know about how a developer chose the tools that they chose, the more assumptions you're able to draw, and the more places in the developer tools you're going to be able to look to find all of this information with relative ease. Attackers will be doing this. Let's take a step back for a moment and talk more generally about web application architecture. This example of the Cyber Scavenger Hunt was built using React and is what we would consider mostly a single-page application, which means that the developer created a JavaScript bundle and a single HTML page. The HTML page executes the JavaScript, which constructs on the client, which is the browser, a fully functioning application that does not need subsequent round trips to re-render the output that appears on the screen. The best analogy for a single page application might be a literal tree, where you can think about the spot where the tree grows out of the ground being the base state of the application when the server first returns the data. Day after day, season after season, user interaction after user interaction, that tree is going to grow all kinds of branches and leaves that allow the user to interact with the application differently depending on the steps that they took to get to that point. The state of the application changes. If you were to refresh the page, the application would revert back to its initial state. The attack surface also grows as the user continues to interact with the application, because the more branches and leaves that appear on the screen, the more data is going to appear in the browser developer tools, and the more information an attacker is going to be able to enumerate. Again, putting together all of the disparate puzzle pieces that they need to build a picture of threats and vulnerabilities. Last but not least, single-page applications provide endless opportunities for user input and interaction, as well as requests going from client to server over defined APIs or WebSockets or a variety of other communication mechanisms. These are all things that attackers are going to look at closely so that they can gather as much information as they can. Well, you may be asking yourself, what other kinds of application architectures might exist? And in the world of web applications, if you're not using a single page application written primarily in JavaScript, you are likely looking at some sort of server-side rendered application. And a great analogy for this might be some sort of large brick and mortar building. Every window of this building provides a different view into the application. But on every page refresh, that page has to be fully reconstructed and its state fully reconstructed. Some windows will be open because they don't require authentication, while other windows may be locked or boarded up and require some sort of authenticated status or specific role beyond the user in order to view what's inside. The HTML returned from the server will fully reconstruct the page, which isn't to say there is no interactivity on a page-by-page basis, but it certainly is nowhere near the degree of interactivity. The discussion of web application architecture also speaks directly to the OWASP Top 10, which we've only scratched the surface on in this course so far. Having a deep understanding of the web application architecture will illuminate many assumptions made by the developers that can help us better understand the threats and vulnerabilities faced by an application. For example, reflected cross-site scripting attacks are going to be hard to spot using automated tools in a single-page application, where they may be easier to spot in a server-side rendered app. Single-page applications are far less likely to interact with XML-based APIs. Server-side rendered applications built with technologies like ASP.NET are likely to be far more reliant on technologies like cookies and HTTP forms. Again, the better you understand the architecture, the better you'll be at identifying threats and vulnerabilities that map to the OWASP Top 10. So that's great general advice, understanding the architecture so you can map things to the OWASP Top 10. Let's get a little bit more specific. How might we better understand the architecture so that we know what things appear from the OWASP Top 10 that we might focus on? Let's develop a threat model for our cyber scavenger hunt to make this more clear. Here we have a rough diagram explaining the architecture of the cyber scavenger hunt. We can see that all of the resources are hosted in AWS. The resources are brought down to the user's browser and construct a single-page application in which there are multiple views. There may be outbound communication to a marketing database, and there's certainly information stored in local storage as well as a session cookie. Once we understand how the application's built, we can start to identify specific areas where the OWASP top 10 are most relevant. Coming from left to right, what we can see is that between our AWS infrastructure and the user's browser, there could be sensitive data exposed either in the assets themselves or in any API responses that could be returning data for the application to use. Once the application is running in the browser, again, there could be some sensitive data exposed in the content of that application, but there could be various areas of the application that aren't well secured. And you may remember our contrived example of the hidden admin page. So broken access control would be a concern of ours. Additionally, the use of any third-party code, libraries like jQuery, or I mentioned we were using React. If any of these third-party libraries are vulnerable to public exploits, they would immediately put our application at risk as well. Last but not least, the reliance on data stored in local storage or cookies might introduce threats of injection or, again, sensitive data exposure, depending on what data is stored in those locations and how it is encoded or encrypted. Once you know how the application is built, developing a threat model is the single best way for you to keep your application secure. In the next lesson, we're going to introduce some more tools for you to identify risks, threats, and vulnerabilities in your application.